Okay, so previously we talked about the Bohr model of the atom, and we talked about how one of the big results of the Bohr model was that we were able to predict and explain the hydrogen line spectrum by assuming that electrons can only occupy very specific discrete states of energy. But there are some problems with the Bohr model. The first is that the Bohr model only accurately predicts the hydrogen line spectrum and doesn't accurately predict the line spectra for heavier atoms. And the second problem with the Bohr model is that electrons aren't actually in these planetary orbits around the nucleus. They're actually waves, which we know from quantum mechanics. So the Bohr model starts to break down because it's just not an accurate prediction of the movement of electrons. So again, our limitations of the Bohr model is that our electrons are not moving in a planetary orbit, only predicts the hydrogen line spectrum, so we need a more accurate theory. And that more accurate theory is quantum mechanics. Okay, so the objective for today's lectures are, first, we're going to talk about the motivation for understanding the behavior of electrons. We're going to talk about the Schrodinger equation, nodes, quantum numbers. The focus of this lecture will be quantum numbers, and finally the Pauli exclusion principle. So first we need to talk about our motivation for studying quantum numbers and atomic orbitals. So why do we care about the behavior of electrons around a nucleus? So the reason why we care is that understanding the behavior of and location of electrons allows us to predict reactivity, which is the foundation for chemistry. So having this very fundamental understanding of the electrons in the atom will ultimately be able to help us to be able to understand the more macroscopic aspects of chemistry. Okay, so this is the Schrodinger wave equation. Because we know that matter has wave-like properties, we can use a wave function to describe the movement of the electrons around the nucleus. This is the Schrodinger wave equation, and this equation was developed to describe the energy states associated with wave functions in a given system. So the full version of the Schrodinger equation is out of the context of this class, so I'll only show you the simplified version. But essentially what this equation is saying is that if you have some Hamiltonian, which we label as h hat, it represents a set of mathematical operations that when carried out will yield the wave function again multiplied by value, and this value is energy. We call this value an eigenvalue. This is a concept that you'll learn in linear algebra if you're interested. So if we solve this Schrodinger equation, then we get a set of wave functions corresponding to different energies. And these wave functions are our orbitals. So the Schrodinger wave equation allows us to solve for the energy states associated with a particular atomic orbital, and the energy determined from this equation is the binding energy of the electron to the nucleus. I wanted to help you visualize what the wave function is. The wave function squared is the probability that you'll find an electron at that point at any given time. This is a 1s orbital, and here they're plotting the probability as a function of distance from the nucleus, and you can see that it's most probable that your electrons are going to be very close to the nucleus, and it gets less and less probable as you move out. So like I mentioned before, the Schrodinger equation gives us lots of different wave functions that correspond to different atomic orbitals. These atomic orbitals are where the electrons are located in a particular atom. And understanding these atomic orbitals, you can understand the nature of the electrons in those orbitals. We use quantum numbers to label these different atomic wave functions. And this is important because the quantum numbers help us understand the properties of the orbitals. So the first three quantum numbers describe the orbital's shape, size or energy, and orientation. And the fourth quantum number describes the direction of the electron spin, m sub s. So quantum numbers are just a nice way of us to keep track of different atomic orbitals and help us understand the properties of the orbitals that electrons occupy. Okay, so One thing that I want to talk about before we talk about quantum numbers is to briefly mention nodes again. We talked about nodes briefly when we were talking about waves, but in quantum mechanics, the definition of a node is a region where the wave function crosses zero, or another way of thinking about it. So if you have zero, if your wave function is equal to zero, that means your wave function squared is equal to zero. So it's a location where there's absolutely zero probability that an electron will be found in that spot. So just to give you an example, this is a wave function that's housed, this is an electron that's just inside of a box, so it has very simple wave functions. And every time the wave function crosses zero, that's a node. So this first energy level doesn't have any nodes. Second has 1, third has 2, fourth has 1, 2, 3, and so forth. So those are our nodes. And there's two different types of nodes for atomic orbitals. You either have radial nodes. Radial nodes is almost like a spherical node where there's no electron density. And you can also have angular nodes. Angular nodes are nodes that are planar. So you can see that you have a whole plane of zero electron density. So radial nodes are spherical, angular nodes are planar. Okay, so let's go ahead and talk about the different quantum numbers. The first is the principal quantum number n. So n is any non-zero integer, and it describes the size and therefore the distance from the nucleus. It also should say describes the energy state. As your principal quantum number increases, the energy of your orbital also increases. And again, n can be any non-zero integer, so it can be 1, 2, 3, 4, 5, 6, etc. The angular momentum quantum number tells you the number of angular nodes. Remember previously we said that an angular node was one of these planar nodes. So the whatever number L is equal to, that's the number of angular nodes that your atomic orbital possesses. The shape of our orbital is very dependent upon our angular momentum quantum number. So if L is 0, we have 0 angular nodes and we have a sphere. If L is 1, we have a p orbital, so we have 1 angular node bisecting the orbital. If L is 2, we have 2 angular nodes and now we have a d orbital. And finally, if L is equal to 3, we have an f orbital and 3 angular nodes. Something that's also important to point out is the rules for the angular momentum quantum number. L can be any value from 0 up to n minus 1. So if n is 1, L has to be 0. If n is 2, L can be 0 or 1. The next quantum number is the magnetic quantum number, or m sub L. The magnetic quantum number defines the orientation of the orbital, and it can range from negative L to 0 up to positive L. So if we have an s orbital, we know that there's 0 angular nodes, and so L is equal to 0 for an s orbital. Therefore, m sub L can also only be 0, which makes sense, right? If you have an s orbital, it's a symmetric sphere. No matter how you turn this s orbital, it's going to look exactly the same. So there's only one possible orientation. If you have a p orbital, L is equal to 1. So m sub L can be negative 1, 0, or 1. You can see that here. So we have 3 unique orientations of our p orbitals along our x, y, and z axis. And finally, if L is equal to 2, or d orbital, m sub L can be negative 2, negative 1, 0, 1, or 2. S orbitals have 1 possible orientation, p orbitals have 3, and d orbitals have 5 possible orientations. So the first 3 principal quantum numbers we talked about, n, our principal quantum number, defines energy. L, our angular momentum quantum number, defines shape. And m sub L, our magnetic quantum number, defines orientation. So the first 3 quantum numbers define the orbital. The fourth quantum number is m sub s, the spin quantum number. And this defines the direction of the electron spinning. So electrons are a charged particle, and when they spin, they create a magnetic field perpendicular to the direction that they're spinning. So if they're spinning one direction, they'll point up, and if they're spinning the opposite direction, they'll point down. So we call this spin up and spin down. It's just referring to the direction that our electrons are spinning. Okay, just to review, they're the first three quantum numbers define the atomic orbital. The first is the principal quantum number. It defines the size and the energy of the orbital and also the distance from the nucleus. And it can be any integer number, 1, 2, 3, 4, up to infinity. Then there's the angular momentum quantum number. It defines the shape of the orbital. It also tells you the number of angular nodes. And it can be anywhere up to n-1, 0 to n-1. So if n is equal to 2, L can be 0 or 1. So if we have n is equal to 2, we can either have a 2s or a 2p orbital. Then we have the magnetic quantum number. It tells you the orientation, and it ranges from negative L to L. And finally, we have the spin quantum number, which defines the direction of the electron spin. It can either be spinning in a positive direction or negative direction. And it can be either plus half or minus 1/2. Okay, so trying to tie all of this together, why quantum numbers are important. One really important principle is what's called the Pauli exclusion principle. So each electron in an atom is described completely by a set of 4 quantum numbers. The first 3 describe the orbital, and the 4th describes the electron spin. And the Pauli exclusion principle says that no 2 electrons in the same atom can have the same 4 quantum numbers. So an atomic orbital can hold a maximum of 2 electrons, and they must have opposing spins. So you have to have, each electron has a unique set of quantum numbers. So what that means is in each orbital, you can only have 2 electrons. So I wanted to just do a couple examples. First, it says how many orbitals in an atom can have the following quantum numbers. N is 2, L is 1. So we know if L is 1 that this is a p orbital. So this is a 2p orbital. Remember that m sub L can be negative L to L, so negative 1, 0, 1. So we have 3 orbitals, and how many electrons can occupy this sublevel? So that's going to be a total of 6 electrons.